recording is rolling, but I'm just gonna do these two on the recording, number 53, 54, just for extra projectile examples. We're just doing a little bit of review here based on how the book is organized. So 53 says a dart player throws a dart horizontally at some speed. The dart hits the board some number of meters below the height the player threw it. How far away is the player from the dartboard? Okay, yeah, so number 53. Now I'll change the numbers so that you have a little bit different, one extra example to look at. But here's what we got. We got a dartboard. We got let's say the origin point of the dart. It's like right here. And maybe we've got a total novice, and this guy is looking at that dartboard saying, I'm going to throw it right at that center because I'm going to hit that center. But this guy forgot about gravity because this is his first dart throw ever. Oh, and this dart actually goes, and it lands like right here. And let's say the amount that he missed it by is, well, approximately the radius of that dartboard, which I'll make up a number. I'll call it 20 centimeters. So 0.20 meters. That would be 20 centimeters, wouldn't it? Let's say you know the throwing speed of this guy. So one way you could do that, suppose somebody grabbed this footage with a cell phone camera and you saw this distance and the time, you could divide that and get the throwing speed, which is sort of backwards what we're solving for, but one way or another, you know the throwing speed. Let's call that, 15 meters per second. Create a number. There we go. Can you figure out how far away this guy was standing from the dartboard? What is x? You know what would be a better question is, if you knew x, could you figure out his throwing speed? Right? I'll do it both ways. So let's do the book version first, and we'll go back. Okay, so let's see. I know just like the last question, when x is equal to vt. So if we knew the time of this whole thing to happen, then we could very quickly get the answer, because what we're solving for, if you know time is, well, we know the horizontal speed. But time is not going to come from this vertical constraint, like how far it fell. It's going to take some time to fall this far in Earth's gravity. So let's start with that. We'll start with vertical information. Vertical. Let's break out that old college equation. H equals 1/2 gt squared. Now, again, I left off the extended version, which is v naught t plus. And the reason I did that is because if you're strictly looking in the vertical direction, if you threw this dart strictly horizontally, then when the dart is leaving your hand, how fast does it start moving up and down? 0, starts from rest. So that's why it just boils down to this, like as if you just dropped the dart, it would fall at same distance and same time. Solve for time. Hey, you know what? Last question, I know this is off camera, but there was a similar question, same setup. Remember I solved for an expression for time? I said, I want to solve this expression. If you're watching the video, you can pause the video and see how that math works out. Because this expression might be handy later on down the road. And oh, here it is. So we already did the work. We already solved for time. Did the algebra steps. It just ends up being this. So let's plug in the known values. I know that the height change is 0.20 meters. That's 20 centimeters. So 0.20 meters. And I know the rate that it falls down is 10 meters per second squared. So what's the time of flight for this dart? Square root of 2 by 0.2 on 10. Oh, it's exactly 0.2 seconds, 0.20 seconds. Ooh, I should have chosen different numbers because that could get confusing, but this is the time in seconds, right? This is the distance in meters. Okay, so that's the time of flight. Okay. So now if you want to figure out how far away this guy is from the dartboard, what you want to do is say, x equals v times t. So we're going to switch over to look horizontal, and say how far this guy was standing is equal to the throwing speed times the time, which is 15 meters per second for this time right here, 0.20 seconds. And that would be, choose 30. I think is that 3 meters? What? 3 meters? Oh yeah, that sounds about right. 3 meters. Yeah, 3.0 meters, which is about 10 floor tiles, right? Pretty close to 3 meters. Right? Guys, go there. Now, what I mentioned at the start of this problem is what would probably be a more reasonable type question is it'd be easy to measure this distance and this distance and back calculate what the throwing speed was, which is actually a lab that you guys did. Do you guys remember those launchers, those ball launchers? Okay. So maybe I'll just do this on a calculator and explain it verbally. But say if you knew this was 3 meters, could you back calculate what the throwing speed was? So you're just doing this whole thing in reverse. Say, well, I know if this went 3 meters. Now you still have to know the time, right? So this whole vertical part would be the same to get the 0.2 second based on this falling distance right here. So you do that, get the second. They say, I wonder what the speed is. Well, if I know this distance, because that's very easy to measure, 3 meters, and divide by the time, which you get based on this drop height, which is this whole piece, divide by 0.2 seconds, that is up 15 meters per second would be the throwing speed, which is what the book started out with anyway. You guys got it? Let's do one more, and then we'll be done with this review. And that is number 54. 2 baseballs were hit with the same speed. Draw graphs of y versus t and x versus t for each ball. Now notice that they gave you 30 degrees and 60 degrees to the horizontal. Is it? And the balls were supposedly hit at the same speed, and look how they landed at the same point. You guys see that? Do you guys remember what is the optimal angle for the furthest distance? What is the optimal angle? It would be 45 degrees, right, from the horizontal. Right? Anytime these two angles add up to 90, the ball is going to go the same distance. The shallower angle, because it has a large horizontal component velocity, but a small time, a small time that would be in the air. The one that was hit at the larger angle, say 60 degrees, is in the air for a long time, but has a very slow horizontal component velocity, and the two effects will end at the same spot. 45 degrees plus 45 degrees adds up to 90, so that's another hint that it might be like maximum value. Right? So the fact that these two add up to 90 degrees tells you they'll land at the same spot for the same speed. Right? So draw a couple of graphs is the thing you're supposed to do. Draw a couple of graphs. The y versus t and x versus t. So yeah, let's do these maybe side by side. So as a function of time, tick, 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 and seconds, what is the y value of the ball in meters? And what is the x value of the ball in meters? Okay. For each of these parabola paths, it says draw separate graphs. So maybe I'll pick a couple of colored pens. Okay. I should make a key. That's what I should do. Let's put a key up here, do a little box. And in pink, I'll do at 30 degrees to the horizontal. And in blue, I'll do at 60 degrees to the horizontal. And see if you can stay a step ahead of me. See if you guys can figure out what these graphs are going to look like. So y versus t and x versus t. Okay. Now y versus t is actually going to look, well, if you're watching the video in the future, then you can pause it and see if you can figure out these graphs yourself. Okay. But just to save you guys a minute in class, move forward with this and show you guys the answers. So the y versus t is basically going to look like what's drawn here. In fact, at a glance, it would be very hard to distinguish it. So at 30 degrees to the horizontal, it reaches this maximum height and then comes back down to the ground as a function of some time. So it hits the ground here, it's at 0 meters, at 0 seconds. Okay. And then maybe it goes like this high. And it will be a parabola as a function of time. It's going to look like this. Okay. Now, is this exactly what this is? Technically, no, although really hard to distinguish because what's physically drawn here is like y versus x, meters versus meters. The graph is meters versus seconds. Ooh, so technically different, but same type shape. Okay. And then the one that was hit at 60 degrees to the horizontal is going to go looks a lot higher. Do something kind of like this. And you could calculate exact values if you wanted to too, but just to get the general shapes, that's what I care about, right? All right, so y versus t looks basically like what's physically going on in the spatial world, like that, both parabolas. What about x versus t? Now, x versus t, we're looking at how far it's moved across as a function of time. And isn't that the same for each one of these? Because, sorry, scratch that, that's not what I meant to say. Doesn't the horizontal component of velocity stay the same all the way across for either one of them? Because gravity doesn't pull right and left, and we're ignoring air drag. So that would effectively do something like this. The horizontal component of velocity is just going to stay the same all the way across. And you could calculate what it is, just take the cosine component and multiply by the original speed. So this would be v times, or maybe I should list that here, v times cosine of 30 degrees. And then for the one that's hit at 60 degrees, similar idea, be like up here. I call this v times cosine of 60 degrees for that value. For that. There you go. That's the answer to that one. Those two graphs. Any questions about those graphs? Why they would look like that? Right. So, like you guys see here, there's a bunch of other review problems. I've recorded those in other videos, so you guys can check those out too if you want to see some of those other solutions.